All right, the last concept of this class is going to be looking at electrochemical cells. And in electrochemical cells, much like water, if you happen to have a drop in the height of the terrain, water will naturally flow, creating a waterfall. And the reason it does that is because we go from a high potential energy, okay, a high gravitational potential energy because we're at a higher height above somewhere else. Water will naturally flow from a high potential energy to a low potential energy, creating a waterfall. And we can even utilize, along with being beautiful, we can utilize that falling water as a way to power turbines and other things and convert that kinetic energy into other types of energy that we can utilize. Well, the same thing is true for electrons. If we have a high potential energy, where it comes to electrical static potential energy, the electrical potential, especially is like Coulomb's law, and there's a lower potential energy with electrostatic forces, electrons will naturally flow from a high potential down to a low potential. And this natural or spontaneous flow creates a flow of electrons, and we call flow of electrons electrical current. Current is the flow of electrons, and that's because they spontaneously flow from a higher potential to a lower potential. So in a battery, we have a higher end to a lower end, and if we close a circuit, that electrical current will flow from a high to a low, and that causes us to be able to take that current to charge or utilize to do any of our different power a lot of our different electronic devices. And that's what the focus of this concept is going to be, is figuring out electrical current based on the different types of reactions that are set up. Now, spontaneous cells are cells that naturally occur, and therefore they have a delta G value that is negative. If you have a delta G value, a Gibbs free energy that is negative, these are spontaneous cells. And that's what a voltaic cell is. A voltaic, or on the national exam, you might also see the word galvanic. Galvanic or voltaic means the same thing. Immediately, if you see a voltaic or galvanic cell described, it is a spontaneous cell. So you can already predict that the delta G will be negative. And that'll cause delta E, or E, and sometimes it's labeled E of cell, electrochemical cell potential, will be positive. So if a cell has a positive voltage, it's a spontaneous cell. It's a cell that naturally occurs. Okay? So here's some different terms and adjectives we use to describe in a cell, but I want to show you a basic diagram of a typical voltaic or galvanic cell setup. So let's look at a chemical reaction where we're going to mix. In one compartment, we are going to have copper solid and copper ion. So to create electrical potential cell, usually we need to create a compartment, two compartments, one in which we have the ionic aqueous substance along with its solid state material. So let's do copper, and we're going to do zinc. So on one side, I'm going to have a copper solution, and in the other compartment, we're going to have a zinc solution. Okay? And then we are also going to put a solid metal material into here, and this is called the electrode. The electrode typically is made with the solid state of that material, so that we have both the solid and its ionic compound state in the same compartment. Now, they don't have to be. The electrode could be made out of anything, but for this reaction where I'm going to have copper solid and copper ions and zinc, we want to make sure that the electrodes are made with that material. So this is going to be made with zinc solid, and this is going to be made with copper solid. All right, so in a typical voltaic cell, you're going to see two compartments, one containing an ion, an aqueous ion, and then usually the metal of that same material. Now, it doesn't have to be, and we'll show different examples with the unit so you get practice with that. Now, the concentration of the ions to be standard cells are going to be 1 molar solution. Same thing with the zinc. We're also going to be working with a temperature that is at 25 degrees Celsius. And we are also going to be working with a pressure of 1 atmosphere. Okay? The last thing we need to do is to connect these two compartments together with a wire. And this wire is where the electrical current will pass through. And usually in the middle there will be a device labeled with a V, and that circle V is usually called a voltmeter. So it'll measure the voltage of this cell combination. All right? Then the last thing we have is a salt bridge, and we'll talk briefly what the salt bridge's purpose is to do here. But this is the typical components of a common Voltaic or galvanic cell. All right? Now, what we have here is we have two reactions that are going to be taking place. We have copper ions plus 2 electrons will produce copper solid, and we have zinc ions plus 2 electrons will produce zinc solid. You'll notice that in both of these reactions, these are the two electrical reactions that are going to take place in each compartment. All right, now we can't have both compartments doing reduction reactions. To have a true redox reactions, you've got to have an oxidation and you've got to have an reduction and oxidation. So one of these reactions we have to flip. Now how do we figure that out? Well, we go, all right, so this has a voltage production of 0.339 volts, and the other one is negative 0.762 volts. All right, so when you're given a listing of electrical cell potentials, one of these reactions has got to be flipped. Well, remember what I said, a spontaneous cell, the voltage of the cell must be a positive number. Well, when we flip a cell potential, if it's positive, if I flip it, it becomes negative. Well, if I were to flip the copper reaction, that would now create a negative voltage with that one, and there would be a negative voltage of the other two. And when we add the two combinations together, that would give me a negative voltage. So that can't happen. So what that tells me is I have to flip the second reaction. All right? 0.762 volts. That on the copper side, what I have happening is I have copper ions becoming copper solid, and therefore because this is the side where we have reduction taking place. On the zinc side, we have the zinc solid becoming zinc ions and 2 electrons. This is the oxidation side. Okay? The oxidation side is called the anode. So this would be the anode of the battery. So sometimes you might be asked to label this. So this would be the anode. And a way to remember it is oxidation starts with a vol, anode starts with a vol. So the side that has oxidation occurring is the anode of the battery. The reduction side is called the cathode. And again, R is a constant, so is C. So this is the cathode. Okay? The transfer electrons. Electrons are going to transfer from one of the substances to the other. Electrical current always flows from the anode to the cathode. So electrical current flows from anode to cathode. So just think of again the alphabet, A to C. So the way the electrical current is going to flow is from the zinc compartment to the copper compartment. Okay? All right. So that's something else they might ask you. Which direction does the electrons flow in this cell potential? Now, the copper ions are becoming copper solid. So what's happening here is in the solution, all these copper ions are, because the electrons are being flown or being placed through that metal, those electrons of the copper ions are going to come together, and these copper ions are going to start to deposit on the outside surface of this electrode. So over time, this electrode is going to gain mass because the copper ions from the solution, with the addition of the electrons flowing into the electrode, are going to now become copper solid. So the electrode is going to begin to gain mass as more copper is going to be fused to the surface of it. Vice versa is true here. This electrode is going to lose mass because the zinc metal that makes up the electrode is going to go into the solution as those electrons are pulled away from that metal. And so now we have a decrease in the cathode, we have a decrease in copper ions, so we have a decrease in positive charge. Well, the electrical conductivity of the solution has to stay electrically neutral. So if the copper ions are losing, if we're losing positive ions, we need to replace those positive ions so that the electrical conductivity of the solution stays the same amount of positive and negative charge. So and this is the final purpose of what's called the salt bridge. The salt bridge is necessary so that the solution concentration stays the same. If not, we are now going to build up an excess amount of charge, and very quickly the battery is going to stop working. So the sodium ions that make up the salt will start to migrate into the cathode to replace the positive copper ions that are lost in the reaction. So a way we can remember that are the cations. The cations of the salt are going to flow into the cathode side of the compartment to replace the cations that are lost. So the cations of the salt bridge, so the only purpose of the salt bridge is not to change what the chemical reaction is, but just to cause the positive and negative charges of the solution to remain electrically neutral. So the cations are going to fill in here to replace those. On the other side, the zinc ions are going to increase in concentration as the zinc metal deteriorates into ions. Therefore, the anions, the negative chloride ions, have to flow in here to keep the solution electrically neutral to, again, offset the increase of the positive charge. So the anions are going to flow into the anode side to, again, keep it electrically neutral. All right, so that is what a standard Voltaic or galvanic cell looks like. The first thing you've got to do is figure out which of the two half reactions to flip. The one that you flip is the anode, okay, side of the battery. It's going to produce electrons, and those electrons will flow to the cathode. The cathode will have a gain of mass in the electrode, and cations will need to flow into that side from the salt bridge to keep the electrical conductivity of the solution set. Vice versa, the anions from the salt bridge will go into the side of the anode to replace the cations that are increasing in solution. And to get the electrical cell potential, after you've flipped the more electrical reduction potential and you add the two cells together, the addition of the two equations is the overall reaction of the cell, and it also gives you the overall voltage of the cell. Okay? And again, all of the potentials, all the energies will be given as reduction reactions. And typically, they will be a metallic ion plus electrons that produce the metallic solid. Not all the cases. Sometimes, like iron 3, you might have a reaction where you have one ion becoming another ion, but you will always have the electrons on the reactant side because these are reduction potentials. So to create this cell, one of these will have to be flipped because both compartments cannot have reduction going on. One must be reduction and one must be oxidation. Okay, so those are the different components of electrical or a galvanic cell that you want to be. The voltmeter should read now a voltage for this iron copper reaction, this copper zinc reaction, my fault. We would expect that the voltmeter would read a voltage of 1.10 volts because that's what we calculated when we added the two values together. So the purpose of the voltmeter is to read that flow of current, and it should read about 1.1 volts. Okay? So, if you have any questions, the next lecture, I don't have any homework on this stuff because it's mainly just concepts. The next lecture will go through the mathematical concepts of how to calculate cell potentials. This is more looking at what a voltaic cell looks like. The next lecture will focus on the mathematical principles and how we can now relate cell potentials and convert a E potential into a G or a K and all those mathematical equations that finishes up this unit on electrochemistry. All right, again, thanks for listening. Oops. Introduce a diagram that so if I take the copper reaction and flip it and now make it be, instead of a reduction potential, it is now an oxidation potential. We have electrons on the product side, and now it would give me a negative voltage, which is something I don't want. I want to actually flip the zinc reaction. So by flipping the zinc reaction, instead of it being negative, by flipping it, it now becomes positive 0.762 volts. The copper reaction we leave, and that has a reduction potential of positive 0.339 volts. So when we are asked to figure out which compartment is the oxidation, which one is the reduction, we want to look at the reduction potentials, and we want to flip the reduction potential and make an oxidation potential. We want to flip the more negative voltage. So whichever voltage is the more negative one is the one that we want to flip. And then we add the two reactions together. Now, one thing you got to be careful of is the number of electrons. If the number of electrons are not the same, we would have to multiply, just like when we balance redox reactions in the last step. But here, both of them are 2 electrons, and so they will cancel. The final reaction should not have any electrons present. So what we get, is we get copper ions plus zinc solid produces zinc ions and copper. You'll notice this reaction is both balanced in atoms and charge. And the voltage of this cell would now be the additions of the 2 other voltages. So 1 carry the 1, 0 carry the 1, and we get 1.11. So we would have a voltage, a cell voltage of positive 1.101 volts. This would be the electrical potential of this cell combination. A couple other things we notice is that in this balanced equation, that 2 electrons are transferred per 1 mole of reaction. Every time 1 mole of this reaction takes place, we are going to transfer, in essence, 2 moles of electrons. All right? And that's something that will be very useful when we get into the equations in the next lecture. So, the more negative of the 2 reduction potentials will be flipped to make it oxidation. So now what that tells me, you understand that. Okay? In that, look up the cell. So, as you can see here, okay, we're going to be working with E naughts, which are standard cell potentials. And again, as we've said before, the temperature of that is going to be 298 Kelvin. The concentration will be 1 molar solutions, and the pressure will be 1 atmospheres. Okay? If it's not standard, then that'll be E with no 0 symbol. But for the most part, we are always going to be working with standard cell potentials. Non-standard ones have pretty much no longer are present in the national exam, or to a large degree. It used to be called the Nernst equation. We'll talk briefly about it in another lecture, but something that is not very vital. We're typically going to be asked to calculate standard cell potentials looking at standard states of the substances. Okay? So, in order to create these cell potentials, these voltages, we had to create a reference cell. Just like usually the ground is the reference height of objects. Anything above the ground level is considered to have electric gravitational potential energy of height. For voltages, the standard cell is the hydrogen cell. This voltage of this cell has been given a voltage of 0. So if you go to your reaction, how does that voltage of that half reaction compared to the hydrogen half reaction. Okay? So as I said already, the voltage of the cell is simply the addition of the oxidation reaction and the reduction. And again, to get the oxidation reaction, we've had to flip its reduction potential. So we've already had to flip its reduction value. And then once we've flipped that sign of that reduction potential, we'll add the two. And if it's a galvanic cell, we should get a positive number, or the E of the cell should be greater than 0 if it's a galvanic or voltaic cell. All right, so here is an example where they ask for you to calculate, okay, the reduction potential of this cell combination. So right here, the cell voltage of this cell is 0.44 volts. Well, right now I know that 2H plus produce H. If I split this reaction into two, I'll notice that the hydrogen reaction, the hydrogen ions are adding 2 electrons. This is the reduction potential. And by its terminology, this reduction voltage has got 0 volts attached to it, which means the iron reaction is an oxidation potential because the electrons are on the reactants, are on the product side. Well, if the E of the cell equals the voltage of the reduction plus the voltage of the oxidation half reactions, I know the voltage of the cell is 0.44 volts. The reduction voltage, the hydrogen reaction, is 0 volts, which now gives me the oxidation voltage of the iron reaction. So if I solve that, I know that the iron reaction, its oxidation potential is positive 0.44 volts. But this would be as an oxidation reaction. And this is where oftentimes they kind of trick you. If they want to know the iron reduction potential, that is going to be the reaction where the iron ions plus 2 electrons becomes iron solid. As a reduction potential, it would not be positive 0.44 volts. As a reduction potential, we would have to change the sign and be negative 0.44 volts. So that would be the electrical reduction potential of the iron cell. So I go to my we predicted that it would be about 0.44 volts, but negative, and the table has it being negative 0.409 volts. So we're off by just about 3 hundredths of a volt, which isn't too bad. So maybe this number is a little bit off from the original value. So that's some things to be aware of. Remember that we have both the reduction and oxidation added together, but if they want the reduction potential and it's the oxidation half reaction, we have to flip it. So you got to be very careful of the sign if you want to know the which reaction we're looking at, the reduction or the oxidation half reactions. Okay, so that's how we calculate electrical cell potentials, and that's how we're able to figure out which side is the anode, which side is the cathode. Again, electrons flow from the anode to the cathode, and how we can calculate the electrical potential voltage of the cells. Of thermodynamics constants, the very last table, table 3, is looking at these standard potential values. These are electrical potential values, and you'll notice that in all of them, that electrons are always on the reactant side. These are called reduction potentials. So this is the amount of electrical potential energy we have as a reduction reaction. Okay? So these values we'll utilize to be able to calculate the electrical chemical cell potential of this combination. So you're going to want to make sure to have this table available to you as we do these lectures the next couple of times. Potentials of these guys. So if I look up copper becoming copper solid, which I think is right here, copper plus 2 electrons produces copper solid. This reaction has a voltage of positive 0.339 volts. And then if I look up the zinc reaction, which is right up here, zinc ions becoming zinc, that is a negative 0.762 volts. All right, so we got 0.339 volts and negative 0.762 volts. Values. You'll notice that when you find it reaching 0, that is the hydrogen reaction. That is the reference cell. So all these other voltages are based off of the hydrogen. And find the iron reaction. Right here, iron 2 becoming iron. We see that the voltage of it is negative 0.049. So it's pretty close. It's pretty close to what we predicted it to be. So maybe the initial number was off.